Okay, this week we're going to start talking about clouds, uh, precipitation, and weather radar. This is just a continuation in the moisture section, really. So let's see what we can learn about these. First, we got to figure out how clouds form. Believe it or not, it's not a simple process. And then from clouds, that precipitation forms from them. So water vapor is invisible. When it's there, we can't see it. Clouds are the visible. They're water. So on average, about 67% of the Earth has clouds. And we're about to learn that every cloud has cloud condensation nuclei in it. What they are, some kind of dirt, really. Volcanic eruptions put some debris in the air, erosion of soils, forest fires, ocean, sea spray, even chimneys and exhausts can put that in the air. This is just kind of a relative picture of the difference between a cloud droplet and a rain droplet. A rain droplet's over 100 times bigger than a cloud droplet. So a rain droplet's going to be much different behavior than a cloud droplet. But you're starting with cloud droplets. When you form a cloud, you have cloud droplets. One of the interesting things is called the curvature effect. On a flat surface, no sweat. When you reach 100% relative humidity, you're having an equal balance of those condensation and evaporation at the same time. However, on a curved surface, it doesn't work. For some reason, curved surfaces want to get rid of the condensated water. They try to push it back into water vapor, much better than a flat surface. As a matter of fact, in order to reach saturation there, you have to be almost at 300% relative humidity. So, since we know it doesn't make 300% relative humidity in our atmosphere, why the heck do we wind up with clouds, which starts with this curved water surface? So here's where these cloud condensation nuclei come in. They get dissolved into that curved little tiny water vapor, and they do a chemical reaction that actually helps keep the water molecules there so that condensation can begin right around 100% or even a little bit less. And the clouds can form pretty readily in that situation. So this is called the solute effect. So you have the curvature effect trying to prevent clouds from forming, the solute effect which keeps the clouds there. And these hygroscopic nuclei can be very, very tiny. And it's interesting that over the plains, more dust, more soil, close to the oceans, more salt. There's another part to this process, ice condensation, ice forming nuclei. So we're going to get into that a little bit now too. Here. First off, water has kinetic energy in it. These droplets don't want to freeze because of that kinetic energy, even though it's below 32 degrees. So there must be something that causes these ice droplets to freeze then. And it's called ice nuclei. Otherwise, you're going to stay liquid way down to the Schaefer point, which is around minus 32 degrees Celsius. So what happens then is you wind up with super cooled water, because in the atmosphere, there's a lot of raindrops that are super cooled until they get in some ice condensation nuclei. The ice condensation nuclei can be salt. Again, it can be kind of form of a dirt. But when it happens, you get freezing of these particles, so you wind up forming ice crystals, which look like this. So now we move from, now that we have ice crystals, so how do they get back to Earth, these precipitation? Well, interestingly, gravity pulls these ice crystals down. air resistance, friction, wants to keep them going back upwards. So you need at some point, these crystals have got to get big enough that they can overcome that friction and begin moving towards Earth, and they reach what they call terminal velocity, and that is basically when friction is balanced by the gravity, that they're just moving at a constant speed. And there are two processes that form precipitation in clouds. Collision coalescence occurs in warm clouds. The other day I had that here. We were temperatures in the mid-70s and pouring down rain, but the clouds were very, very warm. We had very tiny water droplets coming out of them because they were forming there. They were very efficient clouds in way of putting down precipitation. So what happens is you get one of these water droplets gets a little bit bigger because it bumped into a couple particles, and it continues to start to fall, and it picks up more and more water droplets till it gets big enough that it reaches all the way down to the ground. This only happens in warm clouds when temperatures are above freezing. So what the other process is in a cold cloud, Bergeron-Findeisen. So most precipitation will form in the middle to high atmosphere where there's ice. So these ice crystals have formed from ice condensation nuclei, usually around -6 to -10 in that range Celsius where they begin to form. Remember, in the last section we talked about vapor pressure, saturated vapor pressure. It was much greater over water droplets compared to ice crystals. So that means that when you have a water droplet there and an ice crystal next to it, the vapor pressure is going to want to go from that water droplet to the ice crystal because the ice crystal has a lower saturation vapor pressure. So what this basically means is eventually all those water droplets are going to become ice crystals and just help the ice crystals to grow. So the ice crystals get bigger, they get to fall to Earth. That's the Bergeron-Findeisen effect. And you can see here, with time, you're basically losing the water that's in the cloud, and you're getting more and more ice crystals. This is a continuous process. So once the rain and ice crystals leave the base of the cloud, they can either go through unsaturated air, like happens out in the Midwest many times, or out in the West Coast, and you get evaporation and wind up with virga, rain never reaching the ground. Rain, there's the size of it, kind of a flattened sphere, not a teardrop, and it can even break apart if it gets too big. Drizzle's just real tiny in the cloud. Technically, according to the National Weather Service, drizzle does not accumulate, but it can make you wet. Basically comes out of low stratus clouds. Interestingly, snow or ice crystals can be in different shapes depending on the temperature of the air. So, say you were having a snowstorm at your house, and you looked out and you saw big snowflakes, probably dendrites. All of a sudden they changed over maybe to these columns or more solid little shapes. The difference in the amount of snowfall you're getting is huge. When you're having dendrite snowfall, it's fairly fluffy. When you're having more of the solid prism snowfall, it's fairly tiny. Maybe a lot of them, but they're fairly tiny. So you wind up getting much heavier snow when there's dendrites. It's actually a problem that meteorologists face when they're forecasting snowfall, of exactly which type of ice crystal are you going to have falling. Depending on your ice crystal is depending on how much snow is going to fall at your house. And I have been in forecasts where we thought it was going to be dendrites and it turned out to be more prism shapes. And we went from a forecast of 12 inches all the way down to 6 inches. All because of the different size of the ice crystals. And here you can see how the atmosphere works with this. Say you have ice crystals form, Bergeron Findeisen. They're all snow coming down here. And somewhere in the atmosphere is a little warm layer. Now, if you don't have any warm layer, there's going to fall snow all the way down to the ground. But remember, the atmosphere is warming as you go down. And sometimes a warm front has lifted up over the cold layer. Happens all the time. Pushes air up. Warm air is less dense than cold air, so it winds up being on top of it. And if you have just a narrow little wedge of it, it may melt it and then have it go back into sleet. You have a little bigger wedge, but you're still below freezing. At the surface, you may have freezing rain, and eventually, many times, you just have plain old rain, even though it is snowing in the clouds up above you. And here you can see the sounding from that, where it's just below freezing at the lowest level. And look how little, maybe about 3,000 feet above freezing here. That was enough to melt that ice. Radar is just a way of looking at precipitation, or even some other objects in the clouds. There's a velocity mode and a reflectivity mode. Reflectivity mode, we detect the precipitation, or actually we can detect things like bugs sometimes. Velocity mode detects the air motion directly toward or away from the radar. By knowing that, I can tell how the precipitation is moving. It gives me a velocity too. It gives me both the speed and the direction. Here's what it looks like. And yeah, it's not much fun with somebody that doesn't like height like me to want to climb up to the top of that, but I have a few times. Here's just the sound wave and how it changes shape. Just like when a train goes by you or a car speeds past you, you hear a different sound. That's the Doppler effect. And here's the next upgrade we had to the radar, which is dual pole. But I want to go back one. Here's a tornado actually showing up. We talk about tornado vortex signatures and mesocyclones. You can see a mesocyclone here, the rotation. And right in here, there's extreme velocity right next to each other. And here's a hook echo that has formed on the radar as well. Here's a hurricane and dual pole. We'll talk about dual pole in a minute. That's another type of radar that the National Weather Service has deployed. Phased array does not exist in the Weather Service yet. I don't know when it's going to come out. It cost a little more than $1 billion a radar for phased array. What phased array does, it sends out multiple beams all at the same time, so you actually get a continuous view of the atmosphere in every direction. And they're fast. They literally go continually update in a matter of seconds, so that you wind up with extremely detailed pictures of the atmosphere. I used one in an experimental situation for a few weeks when I was in Norman, Oklahoma. We detected a hail in one event. We detected a tornado in another. They can get you both warnings a few minutes quicker than the dual pole conventional Doppler radar that's out there right now. And they're more, but that few minutes so far has not been worth it to fund these. And here's a picture. Rainfall can also be estimated from radar. Here is one in Louisiana from very heavy rain from a tropical system. There are three basic types of clouds. There are cirriform clouds, which are basically wispy, icy clouds, very high up in the atmosphere. Stratiform clouds are layered clouds. And then there are cumuliform clouds. Cumuliform are the heaped up or puffy clouds, like we see. So you can see cloud streets coming off the lakes. Since many of you live in Ohio, if you lived in Northeast Ohio, look at this cloud streak coming right down off Lake Huron, across Lake Erie, and into the northeast part of Ohio. Basically, this is a case where you can get significant snowfalls in the wintertime because you're getting moisture from two lakes coming across your area. Advection fog. say fog, air moves across water that's warmer, we know it's going to warm up, condensation occurs. Actually, in this case, I'm sorry, you're going to move across the cool water. This happens a lot in the springtime, especially in Lake Erie or other lakes. This is an example where warm air has come up, very moist air has come up from the south, hits over the lake, condenses because the lake has cooled that air, and then it forms fog and it just moves on upwards. I had one of these experiences when I was at Florida State, where fog came in off the Gulf of Mexico, and just by the end of, I was watching a high school football game at the time, you couldn't see across the field because the fog had got so thick. So the last thing I wanted to show you a little bit here is a couple tools. First, this is a phase picture from satellite. The yellow or orangish clouds are ice clouds. The bluish clouds are water vapor. So you can see here kind of tops that have gotten higher and are forming more ice, where the other ones are more moist, low level, and may not be as high. So it's a kind of a neat picture that you can actually see the differences between ice and water on this picture. Here is a tornado that occurred in Louisville area. Right here is very strong winds next to each other. Here's the hook echo. And one of the things dual pol does, it gives you a radar picture in 2 dimensions. Before, we just sent out one beam, all in the same direction, all in the same dimension, flat. Now, we send that same pulse, but instead of just being flat, it also has a vertical component, so we can see the shapes. That shape means I can determine if there's a different change of shapes in a small area. And in this case, there is a tremendous difference in a very little area, which relates right to here. And this is debris, tornado debris from that. Depending on how high up you're looking at it, you may not see as much, but closer to the ground, you can really see it picked up. And finally, with that as well, one other aspect of dual pol is you can actually look at hail. Many times you have a very strong thunderstorm. It looks like it's pouring down the rain. And we assumed before we had dual pol radar that there might be some hail in here. And depending on how that looked, what environmental conditions are like, I might forecast it. I might put a warning out for hail. But now I can look at it, and here, for example, on change and the correlation coefficient, CC, it's picking out a change in shape right in here. And that change in shape probably indicates to me that I'm looking at the potential for some hail. And here's KDP, which is just another product derived from it. It actually has a black area in it. That is a very strong indicator of large hail. So with all of that, putting these together, I'd be issuing a severe thunderstorm warning for this. So you can see now how dual pol can be used to enhance what we've been doing. And the dual pol, because it looks at shape, enhances the rainfall. So we can get a much better estimate of how much rain fell. So if you have any questions about this, please don't hesitate to ask.